welcome everyone to today's seminar. Today is a pleasure to have Alexandros Chiotelis, who is a researcher and at the University of Athens, right? And so Alex obtained his diploma in physics from the National and Kapodistrian University of Athens and his master's degree in astrophysics from the Utrecht University in the Netherlands. He then carried out his PhD in Amsterdam on the interaction of type 1a supernova remnants with the circumstellar structures. He then moved back to Greece, where he is now, and he has a position where he does 50% of research and 50% of outreach. So he's involved in many outreach activities. So Alex, it's super nice to have you here. You may start when you're ready.
Yeah, thank you, Anna, very much. It's a double pleasure to be here. Thank you for your kind invitation. Hi, everyone. My name is Alexandros Chiotelis. I'm from the National Observatory of Athens, and as I said, I'm very excited for two reasons. First one, that I'm seeing Anna after so many years. We were together in Utrecht as PhD students. And the second one is that I'm talking to Brazil. My mother was born in Brazil. I have never been. It's one of my life dreams to be there. But it's the first bridge, let's say. At least I'm there through the internet. So what I'm trying to do, my goal today is to talk about supernova remnants and circumstellar structures and discuss together how these two objects interact to each other and what we can learn about this interaction. I'm going to have a brief introduction about supernova and supernova remnants, and this because these two phenomena goes really to the past, in the historical times, where ancient civilizations like the Chinese, the Korean, the Babylonians, and the Greek civilizations were observing, the astronomers were observing a very bright stellar-like objects appearing out of the blue in the night sky, staying there, being brighter and brighter, but then after a couple of months, they were gone as suddenly as they were appearing. And that was quite challenging from the Aristotelian point of view, because according to the Greek philosopher, the celestial world had to be perfect, eternal, and invariable. And this kind of variability of these strange stars that they were appearing in the sky was quite tempting and challenging. And we do have records of these strange stars from the very ancient years. This is an example from the Chinese civilization in the Book of Han, the 2nd century, where I don't know if any of you speak Chinese. I will translate what it says. That is the 2nd year of the epoch of Chongping. This is actually the 2nd century. A guest star appeared in the middle of the Nan moon. It displayed various colors and gradually lessened. In the 6 months of the succeeding year, it disappeared. This, as you can see, is a poetic way to describe a clear supernova phenomenon. And of course, supernova occurred during the regional period that it really confused the astronomers of this period. Here you can see the two famous astronomers, Johannes Kepler and Tycho Brahe. And these astronomers thought that actually this appearance of the guest star is actually the birth of a star. That's why they gave the name to this phenomenon, the stella nova, which means in Latin, a new star. Here you can clearly see the handwritten notes of Tycho Brahe, where he points at the constellation of Cassiopeia that a stellar nova appeared, a new star appeared, and marks it with the letter I. Then we move in our historical discussion to the 20th century, and with two outstanding astronomers, Bade and Zwicky, where first of all they realized that the stellar nova stella, can be classified in two classes: the classical novae and some others that are way more brighter. And since they are more brighter, more luminous, they use the term supernovae. And in this paper in 1934, they wrote something really brilliant. These two scientists are the first people that they realized that actually a supernova represents the transition of an ordinary stars into a neutron stars that is consists mainly of neutrons. Such a star possessed a very small radius and an extremely high density. In just one paragraph, these two scientists predict two very important objects of modern astrophysics, supernovae and neutron stars. So according to them, which is actually the correct point of view, a supernova occurs when we have a large star, a massive star, that collapses under its own gravity into a very small object, a neutron star, which is a couple of kilometers as a radius. And obeying the conservation of energy, the gravitational energy is converting to thermal and kinetic energy. And the thermal and kinetic energy is so tremendous that actually the star becomes gravitationally unbound and explodes. That's why this kind of supernova explosions are called core collapse supernovae, meaning supernova that they are formed by the collapse of the core of the stellar core under its own gravity. So according to Bad and Zwicky, we realize that actually a supernova does not represent a birth of a star, but actually the opposite, the death, the catastrophic stellar explosion that marks the end point of the stellar evolution of specific stars. And supernovae are one of the most energetic phenomena that we have ever seen in our universe, releasing energies up to the 10 to the 51 erg. This energy is comparable to the energy that the sun will radiate during its whole life, during its 4 billion years. And it's so fatal that the stars literally blow apart and ejecting its innards with tremendous velocities. So if we're going to have a look at the position where Tycho Brahe mentioned his nova stella, we will see something like that. Here, what you see, this wonderful, breathtaking nebula, the Tycho Supernova Remnant, is actually the innards of the star that exploded almost 5 centuries ago. And if we see at the regions where the Book of Juan writes that the guest star appears, we will see something similar. We will see again a very nice nebula, which again is the star that exploded almost 2000 years ago. After the work of Zwicky and Badi, the telescope were developed and improved a lot. We could conduct very detailed spectroscopical studies, and we realized that supernova can be classified in several classes based on their early spectra, and especially for the absorption lines. Some of them, they possess very intense hydrogen absorption lines, and this class were named as type 2 supernovae, while others, they don't possess any hydrogen, and they were called type 1 supernovae. But then there are subclasses where when you see also a lot of helium are called type 2b, while when the hydrogen is dominant are the normal type 2. Regarding the hydrogen poor supernovae, we have the type 1b when they are helium rich, and the type 1c when they are helium poor. All of them, however, result by the same physical process, as we described before, by the core collapse of the collapse of the core during the final phases of massive stars. And according to the scientists, the reason that we don't see hydrogen or helium in many cases is that somehow the star lost its hydrogen and helium-rich envelope just prior to the final supernova explosion. However, there is a specific class of supernova, the supernova type 1a, that they do not obey in this scenario. The reason is that the type 1a are characterized by the absence of hydrogen and helium, which again means that their progenitor somehow lost its hydrogen and helium-rich envelope. But the strange thing for the type 1a is that they are met in all galactic types, including the elliptical galaxies. And Anna knows way better than me that in elliptical galaxies there are no massive stars. That means that type 1a resulted by low mass progenitors. And you all know that low mass stars do not evolve as neutron stars. And today there is a consensus that type 1a results by the explosion, the thermonuclear explosion of carbon oxygen white dwarfs that they are getting destabilized through the interaction with a companion star in a binary system. And two main paths have been suggested in the literature, the single degenerate and the double degenerate. According to the single degenerate, the donor star is a non-degenerated star, like a main sequence star or a giant, and through mass transfer, the white dwarf is destabilized and explodes. In the double degenerate scenario, we have two white dwarfs, two compact white dwarfs in a close orbit. They start to rotate around each other. They emit gravitational waves. The system loses energy. They start to approach each other. And finally, they merge, triggering the supernova explosion. As we said, the supernova explosion is tremendous, and the stellar material is ejected with very high supersonic velocities. As a result, the interaction of the supernova, of the stellar material with the ambient medium forms very beautiful nebula called supernova remnants, which are actually the aftermath of supernova explosions. And if you see a simulation how a supernova remnant is formed, here is the position of the star that exploded, the origin of the axis. And you can see that the velocities are that high that actually the stellar material is ejected up to several parsecs around the explosion center. It starts to sweep up the ambient medium and it forms this very nice cell structure when there are two shock waves, an inner and an outer one, and here you can see several waves due to the Reynolds-Taylor instabilities. And if we take a knife and we cut a slide from this 2D simulation we make in 1D, here you can see a typical structure of a supernova remnant. And the inner region is the freely expanding ejecta, the material of the star that is expanding due to the explosion. And then you have two shock waves, the reverse shock, the inner one, which is here, and the forward shock, which is the outer, that accordingly they swept up the stellar material and the ambient medium. So the shocked ejecta and the shocked ambient medium are compressed in two dense cells that are getting also extremely hot, and the border between them is the contact discontinuity, and here is the region where the Rayleigh-Taylor stabilities have a party. So you can see here we have a very dense material and very hot material. That's why the supernova remnants become very bright, mainly in X-rays in their cell. And everything evolves, and the same applies for supernova remnants. And as you can see, as you can think, as time passes, the supernova remnant sweeps up more and more in the stellar medium material, and as a result, it accelerates and cools down. The acceleration of the supernova remnant can be expressed by the expansion parameter, m, which is actually the exponent at the time where the radius of the supernova remnant is proportional to the time, the age of the supernova remnant, to this parameter m. And when the supernova remnant is very young, we consider that is almost moving with a constant velocity. That's why m is equal with 1. But then we have distinctive phases, the so-called shade of Taylor phase, m gets 0.4. It has been decelerated a lot. The snowplow phase with m 0.3, momentum-driven phase. And finally, the remnant merges with the ambient medium and is the end of this phenomenon. And here you can see a more realistic simulation. You can see that the position, the radius of the forward shock as a function of time, of this of the contact discontinuity, and finally of the reverse shock. And it's clearly you can see the remnant decelerate as time proceeds. So that's the part of the introduction. Let's sum up. We have the supernova. We know that is actually the death of the star, not the birth. We have several classes according to their early spectra, but theoretically speaking, there are two ways, two physical processes. The one is the core collapse, where massive stars collapse into neutron stars, and that triggers the explosion. And the other are the thermonuclear, or the type 1a supernova, where the star that explodes is actually a white dwarf. And regarding the supernova remnants, it results by the interaction between the stellar ejecta and the ambient medium. It has a typical structure of two shock waves, and by time it gets decelerated. So this is the story that we used to say to our students and to the public, and everything is, we pretend to be confident and everyone is happy. But you know that in science, there's always a huge but in every field. And of course, it is applied also for the case of supernovae and supernova remnant, because as it happens always, there are severe problems and open questions regarding the nature both of supernova and supernova remnants. Let's have a quick look to these problems. For example, let's go to the supernovae first. The core collapse, as we said, the result by is the end phase of massive stars. But do all massive stars explode? People that they do stellar evolution and binary evolution, they explicitly say no. But we are not certain which of them explode and which not. And taking into account that massive stars, the majority of massive stars are members of binary systems or triple systems, and the interaction between the components can alter substantially the life and evolution of stars, makes the situation even more complicated. And also, as we said, the distinction between the type 2 and type 1 and 1b and 1c is the amount of the mass that the stellar envelope got ejected before the final explosion. That's why the star lost its hydrogen and helium-rich envelope. But the question, which is still open, is how the star lost their massive envelope. And there are two suggestions. The first one suggests that it's due to the intense stellar winds and mass outflows prior to the explosion, or others suggest that it's due to the mass transfer in stellar binary systems. Which one is the correct, or which one is the dominant, is still an open question. And the situation is even worse in case of type 1a or thermonuclear supernova. As I said, we have the single degenerate and the double degenerate, but none of them is capable to reproduce all of the observables we receive from type 1a supernova. So despite decades of research, the nature of the donor star, the mass transfer process, and the explosion mechanism itself of type 1a supernova remain largely unknown. And same applies in supernova remnants. I showed you before a simulation, a very nice simulation with the two shock waves and the Raynaud-Taylor stabilities. So we feel happy that we understand what's going on, but then nature strikes back with monsters like this. This is the VRO, supernova remnant. And as you can clearly see, it deviates substantially from what I showed you before from my simulations. As you can see, it has nothing to do with a spherical supernova remnant. Here it looks more like a Chinese hat, and here it looks like a bowl of ice cream. So it's really beyond the spherical symmetry. And here is also something very strange. Here are X-ray, thermal X-rays. According to my simulations, to our simulations, here you can see that the remnant is expected to be actually vacuum. It's like a very tenuous material, has been expanded to very large radii. So here is almost vacuum and extremely cold. And somehow nature say that this can be X-ray bright, which is crazy. So you can, as you can understand, all of these are headaches for the scientists that they do supernova and supernova remnants. But the good news is that these problems regarding the supernova and the remnants are linked to each other. And the link between them is called circumstellar medium. Circumstellar medium is a key from which we can gain very vital information and try to answer at least some of the open questions that I just described. When we say circumstellar medium, we mean all of these structures that are formed by the mass outflows from the progenitor systems just before the explosion. Due to these mass outflows, they sculpture very complex structures that their properties deviate substantially from the local interstellar medium properties. Here you can see a characteristic example of a Wolf-Rayet star that really he made a mess around it. So the stars before the explosion, they tend to blow material around and forms this sculpture, these structures. So subsequently, when they will explode, the supernova will interact with this modified medium. And the key idea is the following. So we have specific stellar or binary evolution, and each of these evolution is linked with specific circumstellar medium properties. So when the explosion will take place, the supernova will interact with this circumstellar medium, and the results of this interaction can be reflected in the morphology and the dynamics of the supernova remnant. And this is something that we can clearly observe in detail. So reversing this logical sequence from the observations of supernova remnants and making the proper modeling, we can get vital information about the circumstellar medium around the explosion center, and from that we can link with the stellar evolution and models and predict the nature and the evolution of the progenitor star. That's the core of my research, and I'm going to present you some characteristics examples. The most common mass outflow are the known stellar winds. The stars, almost all of them, they suffer by these continuum outflows that emanate from their surface and then create bubbles around them. The stellar winds are characterized by continuous mass outflows. They form circumstellar structures. Here is a simulation by Van Marlen. We can see the evolution of this huge circumstellar structure due to the stellar wind. Here is the main sequence phase in two different snapshots, 1 mega-year and 2 mega-year. Here is the red supergiant phase. You can see a very dense bubble that has been formed during this phase. And here is the Warfire phase. You can see that the very dense wind extended the cavity, even the bubble even more. Put some maths there. We can predict the CSM profile by the mass conservation law, and if the star suffers by a stellar wind, the CSM profile looks like that. At the inner region, due to the mass conservation law, the density drops with the density square. So you can get this nice profile, but since the wind is also supersonic, again we have the structure of these two shock waves, the forward shock and the termination shock, where between them the wind and the ambient medium is compressed. Regarding the density, as you can see from this formula, it is proportional to the mass loss rate, the rate where the star is losing through the wind mass, and the wind terminal velocity, in inverse proportional with the wind terminal velocity. And the good news is that we do know these stellar wind properties for different kind of stars, different evolutionary stages of stars. And for example, stars like AGB or red supergiants or luminous blue variables are characterized by high mass loss rate and low velocities. As a result, we do expect to form dense and small bubbles, as you can see in this case, where the density, the overall density of the bubble is much higher than this of the interstellar medium. On the other hand, when we have main sequence stars or Warfire stars or winds from white dwarfs, these are characterized by low mass loss rate and high velocities, so they will form very extended low density cavities, and the density is way lower than this of the interstellar medium. So when the supernova explosion will occur, initially the shock wave of the supernova remnant will start to penetrate and evolve within this R-2 wind profile. And according to analytical solution, I don't want to bother you too much with them, we do know that the expansion parameter is completely different when the supernova remnant is expanding within a wind bubble than it is expanding in a homogeneous interstellar medium. And specifically in the bubble, the remnant decelerates slower. That's why the expansion parameter is much higher. For example, for the case of supernova 1A, in the bubble, the expansion parameter is 0.8, where if it is expanding in an interstellar medium, the expansion parameter is 0.57. But apart from that, from the expansion parameter, it also, the interaction of the supernova remnant with wind bubbles also affects substantially the structure. Here is one example of a dense bubble, where here you can see the resulting supernova remnant, and in solid is the resulting supernova remnant evolving in a wind bubble, and with the dashed line is the same supernova remnant if it was just interstellar medium. As you can see, since the dense bubble is dense, the supernova remnant exposes a smaller radius, but it is much denser. So it results that the reverse shock is triggered faster and forms a very dense cell. So smaller and denser SNRs are expected to be formed from dense bubbles. In case of cavities, of course, we do expect the opposite. Since the density is very low, the supernova remnant is evolving very fast, and its density is much lower than those that are evolving in homogeneous interstellar medium. And this is not just a theoretical studies, because we have seen supernova remnants that possess exactly the same properties. For example, in the dense bubbles, the properties of the supernova remnants that evolve in dense bubbles, a characteristic case is this of the CAS A. The CAS A has exactly the expansion parameters and the densities that are expected from an evolution within a dense bubble. And by that, we know that this remnant is evolving in the wind bubble of a red supergiant or yellow supergiant progenitor. And also for the case of type 1a supernova, Tycho supernova remnant also show direct evidence that has an interaction history with a dense circumstellar bubble, because its properties can only be explained by considering such an interaction. And this circumstellar bubble, since we are talking about a type 1a, so it means a low mass star, can be either formed by an AGB progenitor, or it could be a planetary nebula, or it could be a common envelope that has been ejected from the binary system. So look at just by these properties that we do expect by the supernova remnant and CSM interaction, we predicted the progenitors of these two remnants. And it's also the case, the same case for extended cavities. And where a characteristic example is this of RCW 86, which is very extended with a very low density, and we do know that this can only be explained considering that the supernova remnant is evolving in a large and extended low density cavity excavated by the progenitor system. And according to our models, we suggest that this cavity was formed by the mass outflows that were emanating from the white dwarf surface. Consequently, and subsequently, when the supernova remnant will evolve with this R-2 profile of the wind bubble, it will collide with the wall of this wind bubble where the compressed stellar wind and ISM is lying. As you can understand, since the remnant is colliding with something very dense, a substantial deceleration is expected. And the deceleration is that high that actually the cooling time scale becomes smaller than the dynamical time scale, meaning that the shock becomes radiative. And here is a characteristic example of Kepler's supernova remnant, this historical supernova remnant. It's a very young, that's why we expect to see bright in X-rays, which is in this figure. But looking at the optical, look at that. We see only radiative shock waves only in this region. And that means that here is interacting with something very dense, which is the wall of the wind bubble. That's why it became radiative. And this fact is reflected also on the expansion parameter. In the rest of the region of the remnant, the expansion parameter is 0.6, while in the northwest is 0.3. There, the remnant has been decelerated substantially. In other words, the remnant in the rest of its region is a young remnant, while here has become way older. Another very interesting result with the collision of the supernova remnant with the density wall of the wind bubble is the formation of reflected shocks. As it is the same with the sound. When the sound wave will collide with the wall, a part of it will start to penetrate the wall, while the rest will be reflected back. It's the same with the supernova remnant. It collides with the wall of the wind bubble. It starts slowly to penetrate and becomes radiative, but then at the same time, a very strong reflected shock is formed. And based on the analytics, these reflected shocks can be very, very fast, that really rapidly starts to move inwards, reaching the center of the supernova remnant. This is a characteristic case of a supernova remnant that a reflected shock has been formed, and which is the K727. Here you can see this region that has been collided with something very dense, and here is the reflected shock that has been triggered by this collision that is moving moving inwards towards the center of the supernova remnant. Based on this idea, we decided to assess, to check whether reflected shocks can be responsible for a very strange class of supernova remnants called mixed morphology supernova remnants. This peculiar class is characterized, are evolved supernova remnants. They are characterized by a cell type in radio, which is synchrotron, and it is expected to be in radio because it has been evolved, so they have been substantially decelerated. But in the inner region, as I show you also for the case of VRO, they are very bright in thermal X-rays. And such a case is completely in contradiction with the standard supernova remnant evolution, because as we explained before, as the remnant evolves and is adiabatically expanded, the interior of the remnant should be cold and with low density. So how in hell this cold, low density interior can be bright in X-rays? So we came with this idea that is actually due to the collision with the density wall and the formation of the reflected shock. Such a structure of a very dense wall can be formed by typical red supergiant progenitors, where these circumstellar medium structures can be sculptured by the evolution of the wind, initially as a main sequence star and then as a red supergiant. And if you put that in the hydrodynamic simulation, you get such a circumstellar medium structure. Here is our little star that exploded as a supernova, and as you will see, the supernova remnant starts to evolve and interact with this circumstellar medium structure. After a while, it collides with the density wall. Here you can see that it has become very bright because it has been substantially decelerated through this collision. So the dynamical age is larger than the cooling age. So the shock wave became radiative. And here is a reflected shock that has been formed. And as you will see, it really rapidly moves inwards. It starts to move inwards and accumulate the whole material of the stellar ejecta at the center of the remnant. So the stellar material is accumulated due to the action of the reflected shock at the inner region of the remnants. And since it has been shocked, it has been heated to very high temperatures, up to the 10 to the 7th and 10 to the 8th Kelvin. In other words, we get a typical structure of a radiative old shock wave in the outer shell, and in the inner region, due to the action of the reflected shock, the material has been accumulated and heated up to temperatures that it became X-ray bright. So reflected shocks and collisions with circumstellar structures can be very promising in explaining this puzzling class of supernova, the so-called mixed morphology supernova remnants. I hope you are still alive. This is the final chapter of my talk. And as you can see in this video, nature would have been very strange if everything were spherical symmetric. And the same applies for stellar winds and supernova remnants. In nature, it's very rare to see very, very nice, smooth, and spherically symmetric circumstellar structures, and we have important deviations from the spherical symmetry, either due to the stellar duplicity or the stellar rotation. The stellar systemic motion also can be responsible, or the action of magnetic fields. And the same applies for supernova remnants, where, again, very rarely we can see nicely smooth and spherical supernova remnants. Most of them, they have peculiar asymmetries. And very common, frequently met features are, for example, bosons, antisymmetric lobes. Here you can see that they look like ears in the morphology of the supernova remnant, or here, or equatorial belts. These are one of the most frequent features that are met in supernova remnants. So the question is how these features of supernova remnants can be linked with specific asymmetries of the circumstellar medium, and through that, what we can learn about the progenitors. And we're going to discuss two of them. The one are the bosons. The bosons are frequently met both in circumstellar structures and in supernova remnants. The reasons that are formed is known, and we know that this can happen in case if the mass-losing star is moving with a tremendous systemic velocity. As a result, the interaction between the flow of the wind and the interstellar medium can form this nice bow-shaped structure. It's a more or less similar phenomenon with this, where a dog takes out its face from the window of the car, and the interaction between the hair of the dog and the wind that is coming to its face forms a very nice bow-shaped structure. So also in case of stars, we have the star, we have a spherically symmetric wind, but at the same time, in the rest frame of the star, we see a flow of air that is coming, the interstellar medium. So the interaction between these two flows and the obey to the ram pressure balance forms these nice bow-shaped structures. And of course, you can understand, depending on the wind properties, the interstellar medium properties, and the velocity of the mass-losing star, different structures can be formed, different bow-shaped structures can be formed. Bosons, as I said, also are met in supernova remnants. Kepler supernova remnant, as we discussed before, possess a very nice bow-shaped structure. Here you can see in the northwest region. So according to that, based on that, we can consider that the progenitor system was a runaway star, and due to that, formed a very nice bow-shaped circumstellar structure. So when the supernova remnant started to evolve, nowadays it's interacting only with the edge of this bow-shaped structure. That's why we see interaction only in the northwest region of the remnant. And the modeling that we conducted almost like 13 years ago can really well reproduce the morphology and the dynamics of the remnant. And the same applied to the youngest cousin of Kepler, the G1.9, where also here you can very nicely see a bow-shaped structure. So based on that and through detailed modeling, we determined that both of the progenitor systems were runaway stars with tremendous velocities that explode, the moment that they exploded had shaped bow-shaped structures. The last one regards the bipolar circumstellar structures. It's quite common in around stars to see these bipolar structures, that this can be like an hourglass or a peanut-shaped structure, and these have been attributed either to stellar rotation, close binary interaction, eruptive mass loss, and also the action of magnetic fields. And regarding the nature of the star that are most frequently met, these bipolar circumstellar structures, this could be luminous blue variables or blue supergiants. And regarding the supernova, type 2 supernova and type 2n supernova are those that we have seen that also possess bipolar structure. The supernova 9087A is one characteristic case. Finally, regarding the low mass regime, planetary nebula, here is characteristic examples, or AGB stars also tend to form bipolar structure. So the question that I was wondering a couple of years ago is like, what if a supernova explosion will take place and subsequently interact with a nice bipolar circumstellar medium structure? What will happen? Which will be the morphology of the resulting supernova remnant? So we decided to conduct some hydrodynamic simulation to have a look how it looks alike, and the result was very surprising. And let's see that together. As it is expected, it starts to evolve, it starts to penetrate. Now, it has been penetrated completely, this bipolar circumstellar structure, but in the equatorial plane, where it was this equatorial belt of the structure, the remnant penetrated this dense belt. We had a shock breakout that actually formed these very nice lobes. And if we let the remnant to evolve, you will see that these lobes will be evolved in very nice opposite lobes. In other terms, the supernova remnant forms two nice antisymmetric ears in their morphology. In other words, we show that this morphological feature of supernova remnants called ears can be resulted by an interaction history of a supernova remnant with a bipolar circumstellar structure. In other words, if you will see a supernova remnant that possessed ears in their morphology, most likely its progenitor had formed a bipolar circumstellar structure well before its final explosion. And we played a bit with that, with the bipolarity of the circumstellar structure. Here you can see a peanut shape or an eye-shaped circumstellar structure, and we simulated the interaction of the supernova remnant with such a circumstellar medium. And here you can see that the peanut case can form these nice equatorial belts that are met in supernova remnants. Here is the simulation. These are observations, while the eye-shaped circumstellar structure can form these nice lobes. This is the work that we conducted with Pablo Velázquez 2 years ago. So, a big breath. We are moving to the conclusions of this talk. We know that the ideal case that we discuss with the students is always a supernova interact with a homogeneous interstellar medium where everything is smooth, homogeneous, and spherically symmetric, but reality deviates substantially from this picture, and the main reason is the circumstellar medium. And this is in line with the stellar evolution theory, according to which we know that the supernova progenitors tends to sculpture their ambient medium through substantial mass outflows prior to the supernova explosion. However, it is very important to study the interaction between the supernova remnants and the circumstellar medium, because through this study we can get vital information about the properties of the circumstellar medium prior to the supernova explosion, and by that we can get vital information about the nature and the evolution of the progenitor star. Characteristic cases, we have shown that the properties of class A can only be explained if the remnant was evolving in a dense bubble of a red supergiant or yellow supergiant progenitor, or the case of RCW 86, which is actually the opposite, that the properties of this remnant can only be explained if it was evolving in an extended low-density cavity excavated by the mass outflows of its white dwarf progenitor. Collisions of supernova remnants with the walls of the circumstellar medium can trigger very strong reflected shocks that can play a very important role in the evolution of the supernova remnant, and our simulation has shown that this process can be very promising in explaining this peculiar class of supernova remnants, the so-called mixed morphology supernova remnants. And finally, I show you that nature hates spherical symmetry. We can see very asymmetry structures that deviate substantially from the spherical symmetry. And when we see bosons, there is a clear indication that the progenitor was a runaway star, while ears and equatorial belts indicate that the supernova remnant had an interaction history with a bipolar circumstellar structure. That were my conclusions. Are an astronomer, but I feel obliged to make some other conclusions as a human being, especially what is happening in my neighborhood. And my final main conclusions is the following: that supernova represents the violent stellar death of certain stars, and this topic is a very intriguing and exciting, but is exactly the opposite when we talk about the violent human deaths. Thank you very much for your attention, and looking forward for your questions. Thank you.
Thank you, Alec. Beautiful talk. Do we have questions from the students here? Do we have, you guys write down something? Or in Zoom until you think about some questions?
I would like to comment, Anna.
Okay, just go ahead. Okay, go ahead, Kepler.
Okay. First of all, thank you very much for the talk. I work on white dwarfs, and I always tell my students that nature does everything that's possible. It's like distribution of possibilities. So there are round ones and there are ones going through a very different systems. And from the ejection material on Betel gas, we know that it's not spherical. The wind has those ears like some of the supernova remnants. So I think it's very important to explore all the possibilities like you did, because everything that is possible will occur, and we have to study all the different situations because it really brings the information that everything occurs in nature. And yeah, I think that especially on one of the things that we have discovered on white dwarfs is that they rotate faster than we thought before. So we just made a study with 800 white dwarfs, and the mean rotation period is about 3 hours. So the ejection will not gonna, the wind and the mass laws are not gonna be spherical. It's gonna be either concentrated on the equator, or for the large fast rotators, or we also found many magnetic ones. So you'll have the bipolar winds. So again, thank you. I really like your results because it is in line with what we are finding every different situation.
Thank you for the comments, and it's very interesting. So if I understood correctly, you saw that also the wind that emanates from the wider surface can be non-spherically symmetric, even if it's a quite fast wind.
Yes, yes.
That's very interesting result.
We don't observe the wind, but we deduce from the fast rotation that is certainly concentrated on the equator for the fast rotators, and for the very high magnetic that we also found. 25% of all the white dwarfs are magnetic, and they have strong fields. So the ejection is going to be bipolar. The prior mass wind is going to be bipolar.
It's very interesting. Is it published, this one, the results?
Yeah, they're both. Well, if you look for Kepler on ADS, my name is Kepler also. So Kepler, in the last 2 years, we have a paper with our students. So Gabriela da Rosa is the one on rotation, and Larissa Amorim is the one on magnetic fields. But I'm the second author on both papers.
It's very interesting. I promise I'm going to have a look, and I will contact you.
Okay, great. Thanks.
Kepler, perhaps you can paste the link of the paper in the chat until we ask more questions. Questions from the audience here, which I think would you like to come closer back?
So, hi, thanks for the very nice talk. So, I like more spectroscopy than images. So that is why my question is related with the spectroscopy. For sure, there should be signals of those shock waves in kinematics and in emission line ratios. So does your model consider that or not?
Oh, yes, yes, because the spectra of the supernova remnants consist of various the X-ray spectra of various emission lines, and these emission lines are time variable, because the ionization age is changing by time. For a characteristic case is for Kepler. The reason that in our modeling we suggested that Kepler had an interaction history with circumstellar medium is exactly to cause a scenario of about Tycho. So we modeled Tycho, and we suggested that Tycho had an interaction history with a dense circumstellar medium based on its X-ray spectra, because its X-ray spectra cannot be reproduced just by considering homogeneous interstellar medium. So Badenes had done that, but if you see his paper, it cannot reproduce with the same interstellar medium density, the dynamics, and the X-ray spectra. If you consider that it had an interaction history with a dense bubble and nowadays is evolving in the homogeneous interstellar medium, then you can reproduce both the spectra and the dynamics. You are absolutely right. The spectra is the most sensitive criteria that we do have to see if our models are correct or not.
Perfect. Thank you.
Great. I'll ask one question. Are there any others from the audience? Okay, so I think you've showed basically supernova remnants from our galaxy. What are there prospects of observing these guys further away? And yeah, what is going on in the field with the new facilities?
Oh yes, there's a big field in subfield in supernova remnants hunters that are the extragalactic supernova remnants. In our neighborhood, like Andromeda or the Magellanic Clouds, we can have a quite high resolution, so we can see the structure, the morphology, the spectra. However, in distant galaxies, we can see them as point sources, which is very important because we can have very well statistics on supernova remnants, but we cannot really talk about morphology or kinematics when we talk about extragalactic supernova remnants in distant galaxies.
And regarding the environments, are there any could there be any methodicity driven differences when you talk
yes.
about these supernova remnants, and that you would probably understand more when you go to other extragalactic environments?
Oh yes, and that's exactly the reason they do statistics, and they can try to predict specific properties as a function of the galactic type, because as you said correctly, the metallicity can play a vital role, or also the initial mass, the stellar population of its galaxy. So yes, it's a very intriguing and growing topic, the extragalactic supernova remnants.
Cool. So if there's no more questions, let's thank Alex again.
Thank you.
And it was a very nice talk. We can go to the other room for a coffee. Unfortunately, you could not join us this time.
Yeah,
Maybe
next time. Okay,
Nice
thank you very
to see
much. Thank you.
Bye.
Bye bye.
Thank you all. Bye-bye.
Thank you. Thank you. Thank you.